Welcome to Study Loop.
Okay, so in this circuit, when the switch is open, we see that the resistors 8.8 ohms and 4.44 ohms are in series connection with each other. So we can, so they will have the same current passing through them. So we can apply the loop rule clockwise. So yeah, so we can apply the clockwise loop rule here to find out the current. Now, starting from the negative terminal, so here this is the negative side, this is the positive side. So now, if that's negative, negative will have negative positive on the capacitor as well. So from here, we'll have negative here, positive here, negative here, and positive here. So yeah, anyway, so let's apply loop rule on the left side of the loop, and starting from negative terminal, we'll have a potential gain, that's why positive V. Then if the current is going in this direction, that means we'll have a potential drop there. So it's going to be minus I is the current that's passing through the resistor, and then there will be a minus R2. So R1 is this 8.8 and R2 is 4.4. So let's write that down here. R1 is 8.8 ohms, R2 is 4.4 ohms. Right, so that should be equal to 0. And if we solve for I from there, we'll get V divided by R1 plus R2. So here V is 24 volts. So if we plug in the values, we'll get current as 1.818 amps. So if we know the current that's passing through the resistors, then the voltage across point A will be the voltage across resistor 4.4, because we need to find the drop across this part only to get to point A. So then it's going to be VA, which is equal to I times R2, and that gives us 1.818 amps times 4.4 ohms, and that's going to be equal to 8 volts. Now the reason we took this one is because we have 0 potential here and 24 here. So if we want to get that, if we want to take this resistor into account, we have to subtract uh, subtract the voltage drop across here from the total or we have to subtract this voltage from the total voltage to get the voltage drop, because we have 0 potential here, and then whatever we get here, that's the potential drop. So we cannot actually take this part while doing our calculation. Right, so that concludes our part A. We concluded the potential drop across A. Now let's move on and see how we can get the potential drop across part B now, or point B. Now in that case, when the switch is open, we have the capacitors, they're in series connection, and if they're in series connection, we'll apply the inverse rule. So it's going to be CEQ, which is equal to 1 over C1 plus 1 over C2, and then let's actually call this one C1 and call this one C2. So yeah, and we should know that if the capacitors are in series connection, then the total charge that we get should be equal to the charge for each individual capacitor. So that means if Q is the total charge, and that should be equal to the charge of C1 and C2. Right. So let's do the calculation here. So as we mentioned, that this is the formula that we should be using, and from there the equivalent capacitance we get as this. Now for Q, or the total charge, it's going to be voltage times the equivalent capacitance, which is 24 times this. Now we're using this voltage because we see that these resistors are in parallel connection with the capacitors, so that means the voltage drop across these two guys will be same as voltage drop across these 2 points. So that's why we're taking 24. So that gives us the total charge, and as we mentioned, that should be equal to Q1 and Q2. Now VB is the voltage across 0.24 microfarad capacitor. So um, sorry, that's going to be 0.36. Yeah, let's strike that out. It's going to be 0.36 microfarad. Right. And if that's the case, then the voltage drop should be Q2, which is the charge that we found out, divided by C2, or the capacitance of the capacitor. So if we divide, so charge will be microcoulomb, and this is in microfarad. So if we do so, we get our voltage as 13.7 volts. So that's our voltage drop across point B. Again, we're taking this part is because we have zero potential around here, so we want to go from zero to whatever we get in point B. So that's why we are taking C2 as our in our calculation. Now, when the switch is closed and after the equilibrium, so when the switch is closed and then after the equilibrium has reached for a long time, there will be no current that's passing through the capacitors, because it's in equilibrium. And then in that case, the resistors will be in series again, and since there's no current passing through this part, so we'll have a series connection of the resistors, and point B will act as a conductor with point A. So that means whatever voltage drop we get in point A should be equal to point B. So that means the voltage across A and B should be 8 volts, and the voltage across C2 should be 8 volts again, because this is C2, and if the drop across this part is 8, this one should be 8 as well, and C1 will be the rest. So what we did here is we subtracted the total voltage from 8 and we got 16 volts. Right. And so for part D, we need to find the charge. Now once the switch is closed, now these two guys are not in series anymore, and what happens is now the charge will be different from each other. And if you want to calculate that, for Q1 we'll have V1 times C1, and we have figured out our V1 from here. So let's actually write those down. So this is going to be V1, this is going to be V2. So V1 times C1 will give us the charge across capacitor 1. So the bottom one was capacitor 1 and the top one is capacitor 2. So sorry, I think it's the opposite. Yeah, the bottom one is capacitor 2 and the top one is capacitor 1. So right, and we figured out the charge that's accumulated on each capacitor. Now when the switch was open, right, so when the switch was open, B had a net charge 0, right, because when the switch was open, what happened was the current was flowing directly from here and here, and they had the equal charge. So the negative and positive canceled each other, so we had a net charge of 0 at point B. And so yeah, that's what we wrote here. So the negative plate of C1 had the same magnitude as the charge on positive plate of C2. And then with the switch closed, these charges are not equal, and the net charge on point B will be the sum of the negative plate of C1 plus the positive plate of C2. So for C2 we'll have the positive, and for C1 we'll have the negative. So it's going to be QB, which is the total charge, and that's minus Q1 plus Q2. And minus Q1 is 0.68 microcoulomb, and positive Q2 is 2.88 microcoulomb, and that gives us minus 4.8 microcoulomb. So that means 4.8 microcoulomb charge has passed through the switch from right to left. So this is left to right. That's why if we get a negative sign, it should be right to left. So it's going to be right to left. Thank you.